Ladies and gentlemen, hello. My name is Anshu. I'm an engineering manager here at Facebook. I'm very excited to be here, by the way. I've loved some of the talks so far. A lot of what I'm going to talk about is going to resonate in terms of content and challenges to what's been discussed so far. So I'm really excited to be talking to a lot of you later today, especially over a beer. So I'm an engineering manager in the Client Foundation org. Our organization is responsible for building tools and infrastructure to improve and defend the health of all Facebook apps. And performance is a major aspect of that health. I'm going to spend some time today discussing performance testing in a lab environment. What was the problem we were trying to solve? How do we do it? And what are some of the challenges we're still trying to tackle? Okay, so this has been touched on in a couple other talks, but I figure I'll do it one more time. So is perf important? Well, we're a bunch of people here at Perf Summit too, so it's pretty obvious that it's important to us. But we're also a collection of data-driven engineers, so let's talk about some data. From studies done here at Facebook, we see a direct correlation of app scroll rate to time users spend in the app. In one case, a 5% drop in scroll perf performance resulted in a 4% drop in time users spend in the app. Even more severe impact is seen in app start. So if cold start for an app goes up by a few seconds, we see a non-trivial drop in end users that are considered active users of the participant, of the platform. The net result of perf degradation is definitely loss of trust by our customers and eventually revenue. Time is literally money in this case, and perf degradation costs real dollars. So we want to build a performance testing infrastructure, but we want to adhere to one of the core tenets of development here at Facebook, which is to move fast. We didn't want to get in the way of the developers unnecessarily. With that in mind, we approach performance testing with the following goals. We want to detect issues early and stop the proverbial performance bleeding before it began. We wanted the results to be repeatable and deterministic. And we wanted to minimize false positives. As Peter mentioned in his talk, a false signal is worse than no signal, and it leads to loss of trust in the platform. So we want to give accurate, actionable results to our developers. So a number of talented engineers tackle these goals by taking a scientific approach to perf testing. Specifically, we would measure performance by carefully controlling the environment that the tests are running in, running the test against individual changes, and doing statistical and ML analysis of the results before giving any signal to developers. So starting with variable control, we controlled for some of the basics. Consistent test accounts are used across all trials with the same data preloaded and cleaned up in between runs. And the infrastructure also triggers staging test runs, where the app to cloud requests are cached and then the responses are replayed. This allows us to replay responses in control and trial runs, and it helps to mitigate server-side performance issues, such as instances that are not warmed up properly. There's a bit more technical complexity involved internally. So our friends at Google and Apple do an amazing job of adapting the performance of devices to optimize the battery experience. But these optimizations unfortunately change the interaction times of the trials. So we solve this problem by using CPU governors to lock the devices at a fixed frequency. We also take a snapshot of the in-memory state of the application during staging and then restore the state ahead of each trial to remove possible caching optimizations that might be happening in between runs. In terms of execution, we want to run control runs with a known good build, and then compare those results against the same number of treatment runs. We want to do this for each experiment and on the same device to control for variability. We also generally run performance tests against a batch of changes. To isolate the specific change, we use a pretty basic bisect strategy, since we want to identify the specific diff and the specific developer with whom we want to engage. So in this diagram, as an example, we see that there's a regression that occurred with a range of diffs. Let's say we executed a perf test at the beginning range, and things were fine, no regression happened. But by the third diff, there was a perf regression that was introduced, and we didn't do another performance run until the very end. In this case, we're going to split the diff range in half and do another performance run and see if we see the same degradation. If we do, then we'll work our way backwards, and if we don't, then we'll work our way forwards. It's a very basic divide and conquer strategy, but it allows us to isolate the specific diff and have a really clear, actionable next step for our developer. Once the results are available, we will do statistical analysis of the data. Ideally, we'd want to generate tons and tons of trials to be able to really guarantee or really be able to ascertain if there's a degradation or not. But in the interest of efficiency, we'll limit the runs to a certain number of trials. And then generate confidence intervals using the bootstrap method to provide a range of possible values. With this in place, we can determine the values between the control and treatment runs that are in the 95% confidence range. After computing the confidence intervals, we cross-compare the results from control and treatment and check the results. So in this case, once we generate the data, what we want to see is each data point is the difference between the control and treatment. In the best case, we would see it hovering around 0 at all times. But then the upper and lower ranges give us the confidence boundaries. So maybe a couple trials were slightly better, a couple trials were slightly worse compared to treatment. Compared to the control. In the red, we see that for one particular run, we consistently see results above the 0 range, which means there's a clear degradation. Further, the confidence lines are also both above the 0 range. This gives us a high probability that this is a clear regression. Running through a few other optimizations we do in the lab very briefly, we remount app data to RAM disk ahead of each run to account for OS level optimizations. We reset the device clock at the same time at the start of each trial to account for possible time to live on the cache entries. We'll clear out possible cache and error logs, and we'll reverse tunnel the logs to an external source to minimize CPU impact of the device. The net result is that we're detecting over 100 confirmed regressions per month. That's pretty cool. Are we ready to declare victory? Not quite yet. The infrastructure is fairly sophisticated, but there's some ongoing challenges we're looking to solve. And I'm going to talk about some of these challenges. They revolve around resolution time, scaling, representativeness, complexity, and humans, all you guys. So let's take a look at the actual developer workflow. So in this case, let's assume that we're using the continuous integration perf test workflow. We start with a developer that's authoring the actual code, and then they submit it for code review to their peers. Alongside with unit integration tests that are triggered. This iteration happens until unit tests are passing and the code reviewers have no more comments, and then eventually the developer lands their code into the main branch. At this point, our perf infrastructure takes over and we run the performance tests. If we notice a degradation, then we do the bisect run, and if we confirm, once we confirm, we file a bug against the developer, and then eventually the developer investigates the issue and fixes it. A very busy workflow. We found that this can take, in the worst case, on the order of weeks to resolve, depending on the release cycle and depending on the complexity of the issue. So to address this, earlier this year, we started experimenting with moving the signal closer to the developers. Specifically, we wanted to try to run performance tests right after the code is submitted for code review. In this case, once again, we begin with a developer that's authoring the code, and then they submit it for code review. At this point, in addition to unit and integration tests, we use static analyzers and test classifiers to identify the ideal performance test to run based on the code that's changed. And for this, we use infer. If we detect a regression, a signal is raised in the same way as unit and integration tests are, without the need of bisecting, because we know the exact diff that's causing the issue. This leads to developers resolving the issue before they land the change in main branch. In this case, the fix time is on the order of hours, instead of days. We know the exact issue when we have the focus of the developer before they've completed their task. So this leads to faster resolution time. So this strategy is clearly more time efficient, but it relies on very accurate algorithms to identify the correct test to run, since time is so critical in this case. And it's something we're continuing to refine. This strategy also introduces another challenge for us, which is scaling. With this infrastructure, we've been fairly successful in identifying regressions, and so we've started to onboard more customers and started to run more and more runs. The more successful we become, the more our test devices have become a bottleneck of the entire ecosystem. It's unfortunately still very expensive to onboard new devices and maintain them in the lab. This challenge is further increased as these devices just reach the end of their life. Sometimes they stop holding a charge, they crash, they can't recover, or they require updates to be applied. Some of these updates, an upgrade on iOS or the latest version of Android, may impact the low-level interactions we use to control the devices. One solution we're exploring is to move some of our workload to emulators and simulators. So this would provide a scalable mechanism for us for more runs, but we're worried about the architectural discrepancy with physical devices. So we're exploring doing some of our performance tests using metrics that we can count. For example, the number of bytes that are read, the number of I/O calls, the number of instructions sent to the CPU, instead of purely measuring wall clock time. Next challenge is representativeness. Our devices are running in the perfect ecosystem with nearly every variable carefully controlled. End users are not running in a perfect environment. They're exposed to a variety of issues, variety of network conditions, and device behaviors. Depending on these conditions vary significantly based on the geography as well. All of our customers are important. And it's critical that we're able to detect performance issues with even more noisy devices. Moving forward, we would like to be able to run our performance tests in a lab that's set up with a set of older devices that are a little bit more noisy. And we then have to adjust our tests to take this into account. So we need to carefully balance how this scales. However, we'd then be able to do some interesting tests around how regressions against these devices compare to regressions that are found with perfect devices. So if a regression happens in the perfect lab environment, it'd be interesting to know if the same issue happens on older devices and vice versa. In that case in particular, there might be some optimization that are running on newer, faster devices that may not show up except on older devices. And that would be really interesting to catch. Related to this, perf bugs are just hard. They require a lot of data, a lot of analysis to resolve, and frankly, a lot of expertise. Perf regressions can happen in the code that's directly changed, but more often than not, it happens in related systems once the code is actually integrated together. This lack of knowledge can result in bug reassignments, asking for more data, or more tests being triggered just to confirm that the issue is still happening. All this higher churn increases the chance of an issue slipping into prod and impacting end users. One of the things we're looking into is if the experience of perf experts can be codified in a scalable manner, and that experience can be used by less experienced developers to resolve perf issues. So if we're able to give hints or insights to non-experts based on the experience of perf experts, that would lead to faster resolution time, and that'd be much more scalable. Examples of such hints might include suggesting performance anti-patterns that might be introduced either through static analysis of the code or similar issues that have been raised in the code as well. We can take a look at data based on sliced impact of users and device profiles. And we can reference prior bugs that occurred in the similar piece of code to see if the tactics used to solve those issues can be applied here. We need to be careful, though, to prioritize these hints to be context aware We couldn't simply blast a list of stuff to developers because then we'd lead to the same problem of focus management of our developers. Finally, tests just become noisy. Bugs are introduced, perf issues can be submitted that just come in barely under the detection threshold. As this noise increases, it requires developers to continually maintain their tests. This is a great intention. I have that intention myself. But building mechanisms to make sure that this situation doesn't happen is very challenging. Oftentimes it requires rules or it requires assertions that we will keep the tests healthy. But people are humans, and sometimes updating a perf test is not the highest priority item on their list. So what do we do about it? Well, ideally, we like to take the humans out of the equation altogether. One strategy we're using is around signal boosting and automated test generation. If we can cover all interaction areas without developers required to do careful orchestration and ongoing maintenance of test cases, we can remove a possible source of noise. And we can dramatically reduce engineering costs. We just give visibility to developers when a regression happens, and they don't have to worry about if the test was noisy or not. They can just trust that a signal was generated. Shangpeng is going to give a great talk around signal boosting later today, so stay tuned for that. Even better would be if we find the regression before it happens. So imagine you're spinning up some code and your IDE identifies a possible perf regression as you're coding it up. Our organization's investment in the next few years is to push performance signals even closer to developers. Ideally, we'd want developers to be able to rely on their IDE for these types of performance signals in the same way that they rely on an IDE to give syntax warnings or simple compilation errors. That, combined with an ability to quickly run tests in the IDE, would go a long way to protecting end users from performance regressions. It would ensure that our developers can continue to move fast without breaking things. If you're interested in learning more, or if you have some suggestions on how we can fix some of the things I talked about, please come find me. I would love to chat with you. Thank you very much. I'll take questions if you have any.
Hi, my name is Samir. I'm from Google. One fact that you mentioned earlier was that you're controlling the environment of these devices, but that, at least for Android devices, requires being root. So is your lab basically rooted devices? Otherwise, how are you able to frequency pin and control various other things on the device?
We're doing a lot of interesting things to the devices. For Android, we use whatever ADB commands we can. We are flashing scripts onto the devices. For iOS, in the past, there was no parallel to ADB. I believe some of the engineers on our team, as well as another team in London, helped to build FB IDB, which is the ADB equivalent to iOS, to be able to have more careful control on the devices. So yeah, we're doing some really interesting things to get low-level granular control of the devices.
This is Brian from Google. You talked about 100 plus confirmed regressions, I think per what, month? Is that
yes.
Yeah. I'm curious about the confirmed regressions part. And what systems do you have in place to actually get confirmation that, yes, this was an actual performance regression, it's been fixed, versus, nope, this was a false positive, versus this was an expected regression? What systems are in place that you can gather the data that you've got?
Yeah, that's a great question. So I glossed over it in the slide, but you could see the confidence intervals in our tests. One of the things that we look for is when a regression was triggered, how close were we to the, were the confidence intervals too large? Meaning, did the trials have too many outliers that made the confidence interval so large that the test is effectively just noisy? There are situations where that can happen. I mean, if interactions happen on the device that we're not expecting, a crash or a dialog pops up that we're not expecting, it could dramatically throw off the metrics marker that we're looking for. So we analyzed that data. We started with just manually looking at it. We would look at the chart and we'd see, oh, was this a one-off? Okay, if it was a one-off, maybe we don't raise signal to developers at all. If we see a trend of issues, yep, that's a legitimate signal. So we used to do this just manually. And then eventually we started classifying these traits and plugging this data into a ML pipeline. From this pipeline, when a regression was raised, we'd get a confidence score on how confident we are that this is a confirmed regression. And if we're highly confident, then we'd raise a signal to the developers. Yes, yeah. The question was if there's a feedback loop that developers can use to indicate that it's a regression or not. There is, and that's used not just for our system, but also as there's a broader initiative in our organization to improve actionability of tasks across perf, reliability, and correctness. And so we use that to gauge what else we can do to improve things, ideally in a fully automated fashion to give high quality signal to developers.
Hi, this is Matt from Snap. You talked about moving tests to basically a pre-merge workflow. What kind of time budget do you give yourselves? Because certainly in our organization, people basically want to merge their code the moment they're done.
Yeah, great question. The answer is ideally 0. So having said that, like we have some rough guidelines on how quickly tests should run to be blocking qualified, meaning they block a developer if an issue happens. And it's on the order of multiple dozens of minutes. It is very aggressive for our test to be able to run that quick. So we're looking at it in a couple different ways. One is, what can we do in our pipeline to reduce the time to execution as much as possible? Since we're currently measuring wall clock time, we can't speed up the interactions. We just have to wait for the interactions to happen. So on physical devices, we'll look at the data to see, using ML analysis, can we detect statistical analysis, based on a test, can we detect a regression with fewer trials? When we started, we said, well, we think we need 50 trials for control, 50 trials for treatment. But now that's becoming really expensive. Can we get away with 10 trials for each? For a high quality test, maybe that's good enough. And that could be a good way for us to move to be a blocking test. And then the other is, if we were to move away from wall clock time, we can measure other interactions that don't require the wall clock and potentially make those tests faster as well. But yes, our developers want to move fast. They don't want anything put in front of them. So the system that we use to identify the test relies on the best tests being picked for diff time signal.
All right. Oh, we have one more question.
Hi, I have 2 small questions. So one is you mentioned about the IDB. So your IDB can do everything that ADB can do. So you can also log the CPU or GPU frequency for iPhones.
I don't know if that's exposed through IDB. I believe we had to use some other scripts for that.
So the answer is yes, you are able to log the GPU and CPU frequency for iPhones.
Yes, but not through IDB. I believe that's a separate script that we use.
Okay. So another question is, so you can catch 100 regressions per month. So how many of them can be fixed by the developers?
Yeah, that's a great question. From my perspective, all of them should be fixable by developers. Realistically, it's very context specific. So we have data that shows that if we wait too long to give developers signal, they're not going to fix the issue because they've moved on. They've context switched, and to context switch back, it's going to take a pretty severe perf issue for them to switch back. So being able to detect an issue faster increases our chance of the issue being fixed. But there's also other situations, like sometimes a regression is introduced not because of the code that's changing on the device, but because of environmental variables. At Facebook, we're constantly running experiments that are changing the environment variables for developers. And in certain situations, those variables may impact the test itself. It manifests as noise in the test, but when you deep dive, you see that the root cause was not simply noise, it was another factor that the test happened to catch. And then in other situations, sometimes the degradation can be specific to a platform. Like there were some cases where there was improvements made on one class of device, which caused degradation in another class of device. This was for that particular issue, the developers were trying to identify if this type of change makes sense. Sometimes it's not clear cut. Like you might cause a 1% degradation in one class in order to gain 2% performance win in another class. So they need to experiment to see what the impact is and then have a hard discussion on if it's the right thing to do.
Okay, thank you so much, Anshu.
Thank you.